You will hear everything you need to know about Kubernetes posture management and runtime protection, ways to secure your software supply chain, managing attack surface reduction, and how to secure Kubernetes with zero trust. Please welcome Mr. Leonid.
Okay, so again, good morning, everybody, and thank you for spending your time on Kubernetes security. My name is Leonid, and in next hour, I will talk to you about what is zero trust, specifically in Kubernetes world, how to achieve it. Probably will help you with some practical advices of how to handle it in your environment. Please feel free to ask the questions. I'll try to run very fast through the presentation so we have enough time at the end to talk about specific issues and questions that you may have during this time. So before we go to zero trust itself, I'd like to get us on the same page with regard to what are we up against? Why are we doing this? What attackers are looking for in the environments that we are protecting, and how they get in and what they do when they get in. Okay, so first of all, data is probably the primary suspect, but it's not the only one. They're looking for keys, they're looking for secrets, they're looking for resources like coin miners is very popular attack vector today to steal your CPU and some other resources. Sometimes they look for damage and extortion type of things. And ransomware is also very financially motivated or they may be looking for intellectual property that you have in your system, some unique algorithms, some unique APIs that you might have, somebody wants to use them. Everything is of value today. Now, if I take many different ways of how they actually break in, how they compromise our systems, I can boil them down into three kind of macro groups. One of them is misconfiguration. You forget to configure something or you misconfigured something, that will be found and utilized. There's a lot of tools in the internet today that will find unprotected bucket or unprotected interface or some sort of potential, web type of attack. Uh, can you still hear me, please? Hello? Can you hear me? Is somebody there? Gentlemen, I see everybody on mute. Okay, I assume you can still hear me. So the other way is a credential abuse, whether it's insider, malicious insider, incompetent insider, unfortunate insider, or just credentials that were incidentally lost somewhere, and they would use them to break into the system. We'll talk about what exactly they'll do when they get there. And the last but not least, probably the biggest and the most problematic one is software vulnerability exploits. The amount of vulnerabilities, exploitable vulnerabilities, is growing by the minute. And you can see in the CVE type of sites how many popular products have critical vulnerabilities with remote code execution, etc. It's not necessarily, by the way, in the container image that you are executing. It could be in Kubernetes itself, it could be on operating system, it could be spread across different components, and you really need to understand how attacker utilizes them and go from one action to another to actually get the whole picture done. Okay, and after they get to our system, most likely they will either abuse some existing software, they'll figure out what bucket was not protected and just go there and get the data from it. They could change the behavior of existing software by, for example, changing configuration, changing environment variables, parameters, etc. Or, of course, they may inject a new software, either by corrupting or compromising the one that you already have inside, or by adding new software components to your system. Okay, again, it doesn't matter which way they get to that point. They can use compromised credentials to run another pod in a Kubernetes cluster, or they may utilize software vulnerability and RCE to inject some malicious executable into the cluster. Okay, this picture is important because we'll get back to it when we talk about protection techniques. Okay, so what is zero trust and why does it help us, or how does it help us? So first of all, I want to say the zero trust is not a destination, is rather a journey. It gets you one step closer. Every action you take gets you one step closer to the promised land. But unfortunately, that promised land keeps going farther and farther away because we always have new vulnerabilities. We always have new attack vectors. Attackers are very clever. They evolve every day, and therefore we need to evolve the protection layers every day. Zero trust is a concept. It says never trust, always verify. Sounds nice. It was invented over 20 years ago, but verify what? Or trust what? What trust, what not to trust? How we can verify it? When should we verify it? And the last but not least is why. Now, during this presentation, we'll talk about what we have to do and how and when, etc., in much more details. But at this point, I want to just spend 1 minute to talk about why. Why do I even need to know why I'm verifying a privileged container or exposed interface? Why is that important to me? You know, people who run antivirus say, I know I need to run antivirus. That's it. I know I need to do it. Do I need to understand every virus for that? Probably not. But when it comes to Kubernetes and you start to assess your Kubernetes security posture, you'll be using what they call security validation frameworks like CIS, like Latecomer and SAFE, which we are in Armor like very much, and I'll explain why in a second. Those frameworks, they'll tell you what to check. Some of them have over 100 different checks, and you need to basically go over them one by one. Do you need to understand why you're doing this? Well, in my opinion, yes, you must understand why you're doing this, because after you run this like CIS framework, you'll get tens or many tens of failed controls. If you're lucky, you may have much more, by the way. And you have to realize or understand what do you do now. All these failed controls, how they affect your own environment, how they affect your own business model. What do you need to fix first? What do you need to fix later? This is why you need to understand why. Okay, and now, of course, let's go and talk about what we check, etc. And the first step to do, or first step to realize how protection scheme works in general, is I always like to talk about this 4C model, which was proposed by Google also several years ago, which is a cloud cluster container code. Well, who cares? They kind of missed the namespace, but it probably didn't fit right with the 4Cs. So let's look at this model and see what is kind of contributed or miscontributed by every layer of this model. Okay, we use cloud to configure our cluster. Okay, we use cloud to get base images for our nodes, and everything that is coming from the cloud provider or data center provider, or the image that we took from some repository for that purpose. Okay, it has to be properly configured. It has to be timely updated. It has to be um, basically monitored all the time throughout the entire execution session. So cloud part is very important. However, there are tools like cloud security posture management, like CSPMs, which understand the existence of Kubernetes inside. But unfortunately, Kubernetes in the cloud is kind of a blind spot for those tools, because there's a collection of different worker nodes and a control plane. The control plane sometimes come from the cloud service provider, so they have a visibility of it and probably do pretty good job in updating and configuring it. But still, there are certain things that you need to make sure. Okay, you need to make sure that audit log is enabled. You need to make sure that anonymous authentication is disabled, ECD is encrypted, etc. And that is kind of a boundary between cloud and the cluster. But once you get to the cluster, the CSPM or cloud view is basically becoming kind of blind, because you have many nodes, and what runs on those nodes may be something different at any moment in time. You don't really know what Kubernetes is going to put where, what is going to decide to run on this particular machine. And therefore, understanding security of Kubernetes itself, even though it runs within broader cloud environment, is very, very important. And it's probably even isolated from the cloud, a broader cloud picture, because some people only use Kubernetes or use majority of their application in Kubernetes. And therefore, much more important for them to understand what is the security situation of their Kubernetes cluster. Okay, so in a cluster level, we see many different controls that we need to look at, like RBAC, like role-based access control, like whether we have anonymous authentication or not, whether we have proper communication between our kubelets and our kube API server, etc., etc. Cluster configuration is very important. Do we properly use namespaces or not? Do we even need to use namespaces or not? Is our cluster multi-tenant or not? And then we'll look at cluster roles versus namespace roles differently. If our cluster is not multi-tenant, we'll care less about it. If our cluster is multi-tenant, we'll care much more about it. Okay, and every step we take towards better posture gets us one step closer to the promised land. Now, the container layer is interesting and different, because container layer is kind of twofold. Okay, sometimes from Kubernetes standpoint, we configure container execution parameters. We say whether this container runs as privileged or not. We say whether its container runs as root or not, what privileges it runs with, what capabilities it runs with, etc., etc. Whether it has access to node or not, node network or not, etc. But this is what Kubernetes can impose on the container. The other side of the container is what software developer put in there. Sometimes software developers put or make certain assumptions about how container is going to run, and use those assumptions in a way that Kubernetes controls are incapable of changing them. So, for example, if your software in the container sets up root access, root ownership of certain file, then Kubernetes cannot change run as root to something else, because container will just simply not work. Okay, and there are many examples like this. Therefore, it's important to understand when we take a lot of containers from third parties. I don't want to use the term public repository, because sometimes you use private repository, but still, MySQL container or Kafka container in there is basically the same as you can get from any other public repository. So we take it from the third party, and we have to understand what they do. We have to understand how to configure them and how to reduce the attack surface. But we have to realize that sometimes we cannot go all the way and basically do everything we want, because the code that runs inside the container will just stop working. Now, when you scan container for vulnerabilities, if it's a publicly known and widely known application like Nginx or some Java, whatever, you'll find a lot of vulnerabilities in it, because people are looking at it and reporting those vulnerabilities. If it's your own application, you'll probably find nothing in there. People who experienced with running containers will also know that when you run many of contemporary pieces of code which are developed in Go and use what they call the Go flat images, you won't see practically any vulnerabilities in there unless a certain version of Go compiler was known for certain vulnerability. And this is why, because a compiler basically compounds everything into one piece. It's very difficult to tell which framework you used or which library you used. And therefore, then the amount of known vulnerabilities in that code will be zero. But it does not mean that you have zero vulnerabilities in there. It means that they're just unknown, or sometimes called like 0 day. Okay, so the security of Kubernetes and security in Kubernetes, there are two different viewpoints that you need to realize, and maybe it's technical realization, maybe it's even organizational. Sometimes security of Kubernetes is carried out by certain team, like infrastructure team, and security of in Kubernetes is basically more taking care of the application team. Sometimes not. There's no rules about this. Okay, but it's important to see the distinction. So we have our misconfigurations, we have credential abuse, we have software vulnerabilities exploited, and let's hit the road. Let's see where it takes us. You've heard the term security is shifting left many times, probably. Well, I'd rather like to say security is extending left, because shifting, it means that left leaves something behind. Security has to start as early as possible. There's no question about it, and this is why we need to look at what do we do. We develop. Let's see what can we do when we develop. Let's see what can we figure out from security wise right upon or during development cycle, so that we don't wait until our container gets to the production and then gets bumped back because it violates some rules that our CISO has set up. Okay, and we'll talk about what tools and what checks we can do at all of these stages. We deploy. We have to figure out what we deploy and where. Do we deploy in dev cluster or do we deploy in prod cluster? How do we distinguish between these clusters? Sometimes people run a lot of validations in the dev cluster, which is pretty much wide open, and then when the product or application gets to the prod, gets bumped out again because there are much more strict rules in production. So we need to understand the distinction between these environments, but these distinctions are not always unnecessary. Sometimes you really need to have broader access to your dev environment. So you really need to understand what is the necessary difference between dev and prod and try to minimize it. And then once you deployed, well, the game is only starting, because if you have vulnerabilities in your code, or you potentially lose your credentials or expose your credentials, things will happen during the execution. Nobody exploits vulnerability when software does not run. It happens when it runs. And so it's not enough to say we have launched a healthy container or container that we thought was healthy. It's not enough to say we have checked our vulnerabilities right after CI/CD 2 months ago. New vulnerabilities came up. We need to monitor continuously and understand what happens inside the cluster during the entire execution session. Okay, so let's take it like step by step. Okay, the first and probably the most obvious step would be what we call the posture scanning. That step verifies your kind of static or pre-deployment status of your application. You have excessive or unused roles in your RBAC, for example. And again, I'm going with the same template, like what, when, and how, which we've mentioned earlier in the discussion. Okay, do you have containers that run as root or privileged containers? Privileged containers in even more dangerous than run as root, because they disable all the underlying security profiles, like for example seccomp and capabilities, etc. Do you have access to your node resources or your host file system or network? Have you configured your file system as immutable? Are you allowed to access Kube API or not? All of these verifications, okay, and of course, have you scanned your vulnerabilities? Do you have lost secrets, and etc., network policies? So you basically check the status of your configuration. There's a lot of different checks, a lot of different controls, and you'll get many results. Some of them will succeed, some of them will fail. Some of your containers must run as root. There's no way to avoid this. How do you treat this? So first of all, you need to do it as early as possible. Then you have more time and more understanding. You also sit closer to developers. Sometimes CISO that look at the cluster cannot understand whether a container must run as root or not. You have to go and find appropriate developer that released this task 3 months ago and doesn't even remember what was there. So it's important to understand, to start early in development, and therefore you need to choose tools that can run in your development, that can run in your staging, even before you get to production. Okay, you can check your repositories, you can check your container registries, don't necessarily have to have cluster to verify many of these things. But of course, when it comes to a production, you have to continuously repeat, continuously check those things over and over again. As I said before, new vulnerabilities come out. You have to figure out how to address them. You have to catch them in time. 3 months ago, when you released that container image, that vulnerability wasn't there. Now it is. You have to address it. Okay, and therefore, again, you need to choose tools that can run in all these different areas of your development and deployment cycle. Okay, and you may use the posture scanners, you may use some RBAC visualization and analysis tools. Sometimes it's admission controllers. We'll talk about them in a second. Okay, that tells you what roles you are not using, for example. Okay, you can use container scanning. You can use, it's very popular now to have plugins or extensions to Visual Studio Code. We've done some survey a couple of months ago. It appears that over 70% of people use Visual Studio Code to edit their, to create and work on their YAML files, and that is very fortunate because the extensions, many, not just us, many people publish extensions to Visual Studio Code which allow you to do verifications very, very early in the process. This is very important. Admission control. Admission control happens when basically when your workload is launched or when certain command in your cluster is executed. So if you want to do kubectl exec and your admission control is configured properly, it will pass through the admission control. And you have to understand whether you allow this or not. Again, not every admission control gives you all of these capabilities, all these flexibilities, but this is the way to look at, okay, or this is the way to aim. Admission control always happens in the cluster. So we basically need cluster for that. It still could be dev cluster or prod cluster. My personal recommendation would be to have admission control in both and just configure them. They usually have to can work in alert mode or deny mode. And I would, in our environments, we always configure admission controller in dev cluster in alert and then in production cluster in deny, and therefore we can basically see what's ahead of us. Admission controllers can basically understand user behavior patterns. These are very important. If some user works 9 to 6, okay, and that still happens, in just Monday to Friday, okay, and suddenly he comes in on Saturday, probably we should consider this as a potential break-in or potential abuse of his credentials. You may, if you look at the RBAC from cloud vendors, you'll have a lot of roles, a lot of basically user or group names that are not used in your environment. It's very important to understand and remove them. You don't need to have anything that is unused in the system. Another personal recommendation I would give you is never ever use cluster admin for your daily operations. In my clusters, in my environment, cluster admin will be rejected. If cluster admin comes and say create pod, it will be rejected. We don't do this because cluster admin is a very dangerous role. And cluster admin, by the way, is not just a role that called cluster admin. There's a hard-coded meaning in Kubernetes to role that called cluster admin. But any other role that has a star in verb or in resource or in binding, okay, will basically consider in our system at least will be considered as a cluster admin role regardless of the name. And my point is that these roles should not be used in a daily operations. They only need to be used when you manage your cluster, when you do something, you create other roles. Everything else has to be very, very specific and targeted to the people, to the job that people need to do. Some roles are bound to namespace. Kubernetes provides that capability, and it's important to use it, especially in the multi-tenant clusters. Some roles are cluster-wide. Again, if you don't have multi-tenancy in the cluster, you can be more easy on this. But if you do, you don't need to use cluster-wide roles for practically anything in the daily operations. Okay. The other thing, or the other kind of group of checks that admission controllers give you is all of these posture validations. All of these checks that we've discussed before now becomes a policy, not just diagnostic. Somebody will tell you, you run this pod as privileged. In admission controller, you can say, no, privileged pods don't start in my system. Okay, and you can block it. Now, obviously, there are exceptions. Therefore, if you run posture scan continuously, and every day you get this notification that specific Nginx pod runs as privileged, and you need to run it as privileged. You can set up exception, and normally if the product is decent, then you'll get the exception in one place, and they'll be also helping you in the other. You won't have to configure exceptions in 10 different places. But it's important to configure the system towards your needs. This is why you need to understand why. Okay, every kind of misconfiguration has a meaning, and it's more valuable if you understand how that translates to your specific environment. Okay, you can limit containers that didn't pass through vulnerability scanning. You can, for example, if you have PCI DSS regulation, then you have a critical vulnerability that lasts more than 30 days in your environment, that known to you more than 30 days, you have to stop that container from going up. Okay, and these are the rules that you can basically set in the admission controller, and every such rule will give you one step closer to the promised line. And then, of course, we come to the runtime. Okay, the first thing before we even get to runtime specific issues, okay, it's important to understand that a lot of configuration parameters in your cluster are not visible on the declaration layer. Your YAMLs declare what they need to declare towards Kubernetes to make Kubernetes work. You'll see, for example, if you install Elasticsearch Lake, you will see the service for the master nodes because somebody in cluster need to talk to them, but you will not see anything related to inside the lake communication. Basically, those are familiar with the configuration, the 9200 port will not be declared in the Kubernetes layer, not only because it's not necessary, but also sometimes the way Kubernetes works with services may be potentially harmful to multi-node distributed systems like Elastic or Cassandra or similar. Okay, and so it is important to get this, to know this, even though it's not declared in Kubernetes layer. For people who try to protect their environment, they have to know every port that is opened, whether it's declared in Kubernetes or not. And runtime kind of visibility, live visibility of what really happens inside the containers during the execution is very important part that enriches your understanding of your posture. Okay, and then of course, usual suspects like network policy enforcement. Okay, you have to set network policies because you want to limit potential spread of malicious software. We'll talk about this in a second and see what the meaning of this. Okay, you figure out what executable modules are actually going up, and you can set up some sort of allow or deny list on that. Okay, you need to have some tools for this. It's not something that's provided by Kubernetes, but most of the Kubernetes security products would give you that capability. Okay, a privilege execution tracking, privilege escalation tracking, sorry, file integrity management, software identity validation. We'll talk about this in a minute in much more details. It's a very important subject. Okay, software configuration validation. Remember, we said software may be misconfigured. That would be enough to compromise the environment. Okay, some behavioral type of EDR, XDR, etc. And of course, figuring out whether your SecCom profile is up to what your application really needs. It's closed enough or not. Again, runtime happens in the cluster, but still can be development cluster or production cluster. So we have to distinguish between them. And you have Kubernetes native security controls that you can use, for example, for network policy. You may use some more flexible and more kind of secure products like Istio, Service Mesh, or others. Okay, these are not the only ones, but these are pretty well-known ones. You may have like daemon set agents that usually provided by security platforms like Kubescape, like Aqua, like Breach Crew, etc. You have audit log analysis. So you basically, if you configured audit log properly, then now you get information that you can run through and see what happens in your cluster. Is somebody trying to do something that he was not allowed to do? Somebody tries to create pod, gets denied. Okay, it didn't cause any damage, but you better know that this is happening. You better know that somebody is trying to do something in your cluster that was denied because that somebody is either poor worker that cannot do his job, or somebody inappropriate that try to do damage. Okay, and things like detection and response, like ADR or XDR. So say we did all that, okay, and every single step, as I said, took us one step closer to what we need to achieve in the zero trust environment. Now we have less workloads running as privileged, so they can cause less damage. We have network policy, that means that a spread can go in certain way and cannot go in other way. Say we have all that, and we have a lot of sources of the information. How do we deal with this? How do we treat it? And literally, if you run frameworks like CIS or NSA or whatever, you'll get tens, if not hundreds, of different workloads in your cluster that failed. It's also not just a function of number of controls in a framework, it's also a function of number of workloads or pods in your cluster, basically. The context is very important. If I have critical vulnerability in my container image, it's bad. If I have critical vulnerability in my container image that is configured to communicate with the outside world, is worse. If that container is configured to run as privilege, is really a disaster. And that context is very, very important. This is why I would recommend you to consider the tools that you are going to use, because yes, you can have a CIS scanner which works standalone, and you know what is your CIS diagnosis. Okay, and then you can take a standalone admission controller that will give you certain policy or ability to define certain policies. But only wide platforms that understand all of these angles or most of these angles will allow you to actually combine all this information and say, I've got this from my image scanning, I've got this from my posture scanning, I've got this from my cluster configuration, this is what my runtime told me. Where is the risk? What I'm doing tomorrow morning when I come to the office to fix my system, to make it better. You can close a lot of unprivileged containers, and that may not actually improve your posture because you close them in the places that were not really dangerous in the first place. Okay, so context is very, very important, and contextual risk is very, very important. So say we've done all that. Have we finished or not? My point is that definitely we didn't. And I want to talk about elephant in the room because it's very, very important to understand. We've scanned our images, we've minimized or completely removed number of images that runs as privileged or root. We have no host access, we have no service account that allows us to talk to Kubernetes. We have network policy as good as we can get it, okay? We have network anomaly detection tools, which is even more powerful. We don't have any unused secrets, we don't have any unused volumes, okay? We have to figure, and why are we doing all that? That's the most important question. Why we did all that? What are we afraid of? MySQL runs as root, so what? It will not do any damage running as root. Okay, I have a service account that is mapped to my I don't know Kafka or some secret, unused secret that mapped to Kafka. So what? It will not use it. It's not designed to do it. It's not configured to do it. Why would I care? And the answer is obvious. All of these things we do because we're afraid of compromised software. If my software gets compromised, then those things become dangerous. Before that, they are not dangerous. This is why I said, if you have privileged container somewhere in the basement that doesn't communicate with anyone, doesn't have any access to some sensitive information, it's privileged. Wow, leave it. Figure out where the more dangerous place is and fix that. Everything is contextual, and the key point is that compromised software is the one that causes the most of the headache and most of the potential pain. So We can minimize all these attack angles and still live with potentially compromised software, with zero-day attacks or with known vulnerabilities that get exploited in 5 minutes by the attacker and takes us about 20 days to, in average industry today, to actually update them. Okay, some people take much more. I've seen customers who are running Linux images that went out of support window over a year ago. So you can imagine how old they are and how dangerous is that. So there are several ways to deal with the compromised software, but look at what software does. Okay, when software runs its application or some service, what it does is basically three things. It executes an algorithm that it was designed to do. It reads some files, it reads some secrets, as a sensitive file example, and it calls others, it calls interfaces. And you can basically take a very complicated system and break it down into the pieces like this. This is kind of a atomic unit, like a molecule of the software architecture. Okay, and the question is, who is calling my APIs? Who is reading my data? Do I really know who is doing that? Is that a legitimate software or is it a compromised software? I don't really care whether it's compromised by broken or abused credentials, or it's compromised because of exploited vulnerability. What I care about is this software legitimate or not? This is very, very important part to understand. After we've configured our posture, set up our admission controller, monitoring our system, what do we see? Do we see this or not? Okay, and unfortunately, the technology is not yet at the point where you can continuously verify that your software is legitimate. Well, at least not was there until recently. So here, the model, the Armo Zero Trust model that I kind of wanted to present you. Okay, we have built a system where basically a new technology that allows us to continuously verify cryptographic integrity of every piece of software that runs inside your containers. And as I said before, that's what we worry about. We worry about our software being not compromised as a code, not compromised as a configuration. Okay, and this is what this we call this a software DNA technology, which basically maps all the executables, all the script files, all the configuration files, environment variables, command line parameters for every process that starts in your pod. And pod is very complicated entity. It has multiple containers. Each container may have multiple processes. You have to, it's a very, very heavy mapping task. But at the end of the day, all of these artifacts are snapshot and signed cryptographically and continuously verified during the execution. The verification during the execution is the key here, because as I said before, the vulnerabilities are exploited while the software runs. And being able to know at every moment in time that your software is not compromised gives you a lot of assurance that your entire system, even if sometimes not always configured properly, either because you missed it or because you couldn't do it better, the runtime protection of software identity will give you another layer or another line of defense that is additional to what you have, and it's very, very powerful. And now, the way we can use that line of defense is also very important. What we can basically do with this is to make sure that only workloads that are signed and verified, that are healthy and authorized, can communicate with one another. The only workloads that are signed and healthy can access data in files using transparent data encryption method. And that is what we call the true zero trust model, because now at every moment in time, you know that you're not only talking to MySQL, you know that you're talking to healthy MySQL. And it's mutual. That MySQL knows that you are healthy. It knows who you are, knows that you are not compromised. throughout your entire execution session. This is why we call it the true zero trust, and this is continuous. Okay. Now, this does not replace your activities with the posture. It's very important to do every step in the way, to do it right, because obviously every improvement that we made on the posture, every improvement that we made on the admission, and every improvement that we made on monitoring makes us one step closer. And this is a final or last line of defense, if you wish, which gives you even better assurance. Okay, and this is very much aligned with the concept of zero trust, because as they say, don't trust, verify. So you can always verify. Now remember this one. Okay, why did I make the distinction between reading the files and accessing the APIs? Well, because files are dormant, they don't talk to you. You just read them. They have no way of saying no. When you access the interface is active entity. It can authenticate you. It can require you to actually do something, while just reading the files is much more difficult to protect. And this is why we do it with the encryption. Basically, encrypt files. Transparent encryption means that application doesn't need to know that it's being done, like in a similar concept to a sidecar, where the application speaks TCP and the sidecar turns it to TLS. We've kind of developed the same concept for file access. And therefore, only if application is authorized to decrypt that file, it will get it properly. Otherwise, it will still get it encrypted. Now, this is the example of, I took a snapshot from the real customer. Okay, it's pretty big customer, about 300 different workloads in one namespace. And the reason I brought it is because, good luck defining network policies with that. Not only because there are many connections there, but also because imagine that there is a company that develops such a big system. What is the change velocity? Every day, many different workloads are changing in the system. Every day, a new communication line comes up and goes out. And you not only need to enable the new one, you also need to disable the old one. How exactly are you going to do this? Are you going to have completely separate system where there is no security, so you can figure out who now talks to whom? This is very, very difficult. This is why this model, the basic zero trust model, is such efficient, because you say, okay, if workload A is not supposed to talk to workload B, it won't do it. In order in order for attacker to actually trigger that, they need to compromise the workload identity. And this is why protection of identity gives you much better coverage, much better assurance that even before it gets to do something bad, we already know that its workload is bad. So basically look at this as trying to figure out whether what workload is good or bad based on what it does versus based on what it is. This model checks based on what it is, and it's much easier, much faster, much more deterministic, and much less false positives. If signature of executable file or script file is wrong, it's wrong. It cannot be incidental. It's very, very important, and I think this is where the future of zero trust is going. Okay, the other example I wanted to give you is example of Kubernetes secret lifecycle. Okay, and what I wanted to say here is that the secret lifecycle goes way beyond Kubernetes boundaries. The secret gets created, and before it gets to Kubernetes, has to be somewhere in the YAML files, in the script files, has to be backed up somewhere. It has to go to some Git or other software repository. Only after a while, it will be loaded to Kubernetes secrets. Okay, and will sit in etcd, either clear or globally encrypted. Doesn't bring too much security, unfortunately. Okay, and when the workload starts, it will be mapped to a temporary file to that application. And throughout this entire cycle, this secret is unprotected. So if you do it in a backup and other systems, you have to have another protection system to actually do it, not just the Kubernetes one, but also pre-Kubernetes one. So the way that our file or secret encryption works is that secret gets encrypted basically right after it's created, and then you can put it anywhere because it's already encrypted. It gets encrypted in this, repositories and backups and everywhere. It's protected. There's no worry about it. When it's loaded to Kubernetes, it's also already encrypted. And you define the permissions based on this workload identity that we have discussed, rather than on the name of a pod or container. And then when it's mapped to a temporary file, it remains encrypted. Only when valid and verified application reads that file, that secret gets decrypted. So it basically gives you a very convenient way of dealing with secrets, because Kubernetes secrets is very convenient and it's very much aligned with the rest of the things that you do in your Kubernetes environment. But it also gives you a protection which is completely transparent for your applications. That's it for today. Thank you very much, and I'll be happy to answer questions if you have them.
Could you elaborate how the network policies are created automatically?
Yes. Okay. There are two ways to create network policies. There are several ways to enforce network policies first. One way is to use Kubernetes native network policy mechanism, which basically allows you to say which workload can talk to which workload on the IP base or Kubernetes label base. The slight problem with this approach is for as long as you stay within the cluster and you can basically treat workloads by their labels, their attributes, it's pretty good. But when you start talking to outside of your cluster, then you basically hit the problem. And if you define Kubernetes network policy, especially the egress one, you have to say exactly who you want to talk to. Sometimes when you communicate with platform services, it's very, very difficult to define. This is why I would normally recommend to use ingress policies. It's much easier to define, much easier to figure out who talks to me, okay, especially within the cluster. And therefore, you can use selectors. We can use basically a label of a workload that can communicate with you. Okay, the automatic way of creation of such policy is usually based on gathering the actual communication information. So basically, as you saw the graph that we built for the communication between the workloads, we then take this graph, we see who talks to whom, and we automatically generate ingress policies for those who receives the calls from within the cluster. The other way, the other way that I mentioned was using Armo True Zero Trust technology, is basically built on the fact that we can protect the identity of the workload rather than actual policy. The policy is there. All the communication is TLS, but the policy says whoever is healthy and authorized to communicate in general can talk to me. Now, if A can talk to B, but should talk to B or should not talk to C, as long as A is still healthy, it will never even try to talk to C. To make it talk to C, you need to compromise it. And before you actually get to talk to C, you'll compromise the identity. So we'll know this is unhealthy workload, and therefore it will be prevented from talking. And this way, it's a very, very easy way to define a communication policy, both in a completely automatic way. Does that make sense?
Okay, thank you. Here are some comments or some questions. One comment, very interesting comment, thank you. And another question, I'm curious about how the secrets encrypted in a memory of the app. Needs to use the library, or you are using some kind of sidecar of transparency approach?
Well, it's similar to sidecar. Yes, it's a CSI volume basically. Okay, but the secrets are not encrypted in the memory of the application. Obviously, application needs to use them. Secrets are encrypted all the way before they get to the memory of the application. But at the time when they are decrypted and sit in the memory of the application itself is under close watch of the identity verification mechanism. So if some unknown SO file or unknown script file is trying to get to application memory, that will be identified as a break-in and application will be stopped. Okay. And when I say will be stopped, basically it's a user choice. It's not our choice. We allow user to stop it or to warn about it. It's all flexible. But kind of the most extreme scenario is the identity verification mechanism can stop application when it identifies a potential break-in, and therefore, for as long as secret is open in the memory, the application memory is being verified, and we know it's healthy. Okay.
Okay, thank you very much. Another question: does your solution work with multi-tier Antrea network policy ANP?
I'm not sure I'm familiar what that means.
Okay, another question. I guess the identity is based on the container image signatures. Thanks. CSI volume explains that. Oh, that's probably okay.
Well, the identity is not necessarily based on the container. Well, a container image is part of it, but it's not really the crucial part, because when application goes from the storage, from the image of the container to the memory, it gets changed, and you cannot basically verify the same signature that you have on the file and you have in the memory during the execution. Therefore, it's a different algorithm, and the identity is based on the cryptographic snapshot or specific algorithm that we have designed to snapshot executable files in a way that we can verify this signature while the file is running in the memory.